So we're continuing our partial fraction decomposition. We have one here that has already had the denominator factored for us. So do we have any linear factors in our denominator? Okay, what's linear? X plus 2 is linear. Sure what happened there. There we go. All right, so x plus 2 is linear. And how about the x minus 3 quantity squared? We talked yesterday, right? This is linear. If we squared it, if we expanded it back out, it would be a quadratic. But it's not an irreducible quadratic because we can factor it down, right? It becomes the x minus 3 quantity squared. So both of those x minus 3's are linear. It's just saying we have repeated ones, right? They're in there more than once. So everything is linear. When we break this down into its pieces, its partial fractions, we need a fraction for each of those denominators. So we're going to need 1 for the x plus 2. Then we're going to need 1 for the x minus 3. And then what? Great. We need another one for the x minus 3 squared, right? What if that had been a fifth power instead of a square? Then you're going to have 5 pieces, right? 1 for the first power, second power, third power, fourth power, fifth power. Okay. They are all linear, so in the numerators we just have what? Just the constants, a, b, and c. Yep. Okay. What's the next step? Good. Times everything by the LCD. In this case, our LCD is an x plus 2 and an x minus 3 squared. So on the left side, sorry, I just realized I'm missing a square there. On the left side, everything in the bottom drops out. Okay, so we end up with 5x squared minus 21x plus 13. What happens to the a? What's left that gets multiplied to the a? Good. Okay, what gets multiplied to the b? An x plus 2, and then one of the x minus 3's, right? Because just one of them drops out. And then for the c, just an x plus 2. Okay, so the next step is to FOIL all that stuff out, distribute, right? Expand everything. Okay, so what happens if we take x minus 3 and square it? We get an x squared minus 6x plus 9. So now we have to times a to all of those. So we have an ax squared minus 6ax plus 9a. We good with that? Okay. For the b piece, what do we get if we FOIL x plus 2 and x minus 3? Okay, so now times b to those pieces. So we have bx squared minus bx minus 6b. And our last piece, we just have to distribute cx plus 2c. Are we okay with the algebra of that? All right. Now, yesterday I said you can physically move all these pieces around and regroup them if you want. If you can go through and just pick out the things you need for each equation, I'm okay with that as well. So, for example, on this one, our 5x squared over on the left side has to balance with any of the x squareds on the right. Yes? So, find your x squareds. You've got a of them here, b of them here, and that's it. So, the 5 on this side has to balance with the a plus b on that side? Yes? Okay, I'm actually going to rewrite this so that it's more in our normal matrix format. Okay, so the a plus b has to balance with the 5. Now let's find any x's. We have negative 21 of them over on this side. What do we have on the right-hand side? Negative 6a of them, negative b of them, and positive c. So negative 6a minus b plus c has to balance with a negative 21. We good with that? All right. Last step is our constants. We have 9a's, negative 6b's, and 2c's. Okay. 9a's, negative 6b's, and 2c's. And it has to balance with the 13 over there. Yes? Okay. Now, we could solve this algebraically, but when I first glance at it, I've got 3 different variables. I don't have an equation where I automatically know one variable right away, so it's probably just as fast to use a matrix. You have 2 options. You can set it up as an augmented matrix and do your RREF, or you can set up a coefficient matrix, a constant matrix, and do that inverse of your coefficient times your constant. However you want to do it. I'm okay with either one. I'm going to set up, I think, an augmented one for this. So what would the augmented look like? 1, 1, 0, 5. Okay, second row would be negative 6, negative 1, 1, negative 21. And bottom row 9, negative 6, 2, and 13. All right, so use your RREF. Let's see what we get for A, B, and C. So what do we get for that last column? I see a 3, 2, negative 1. Agree? Okay, and you're going to get those same numbers, right, regardless of whether you used augmented or inverse matrix. Okay, so that tells me that A is 3, B is 2, and C is negative 1. So I would give my final answer. This is my original question, and what did we have? An x plus 2 and an x minus 3 squared. So the first fraction had the x plus 2. The second fraction had an x minus 3, and the third one had an x minus 3 squared. Okay, and we had the A, B, and C on the top. So we'd have a 3 on top of that one, 2 on top of the middle, and a negative 1 on top of the last one. Questions on example, whatever that was? We good with that? Okay. Let's skip to example 5 here. You should have 4 from yesterday in your notes already. Look at your denominator. It's been factored for you. What kind of factors do we end up with? Irreducible quadratics, right? X squared plus 1 can't be reduced anymore. How many of those x squared plus 1s do we have? Dose. Okay, 2 of them. So when we break this into its pieces, we are going to need how many fractions? 2. One that's going to have the x squared plus 1 on the bottom, and the other one that's going to have an x squared plus 1 quantity squared. And because they are irreducible quadratics, what kind of numerators are we going to have? We're going to have linear, the ax plus b kind of thing, right? So let's do an ax plus b in the first one, and then cx plus d in the second one. Okay? All right, let's multiply by our LCD. So everything drops out on the first one. We have 2x cubed minus x squared plus 5x. Then what? Our ax plus b is going to get multiplied by one of the x squared plus 1s. Okay. What about the cx plus d? Doesn't have to be multiplied by anything, right? The whole denominator dropped out. Okay, let's FOIL this ax plus b with the x squared plus 1. Ax times x squared would be ax cubed. Outsides would get me an ax. Insides, we get bx squared. And last, we get b. And then we had the cx and the d that didn't need to change. All right, let's get our things balanced. So let's start with our cubes. We have 2 of them on this side having to balance with what? Just an a on that side, right? So right away we know that a is going to be 2. That was easy. All right, how about the x squareds? I have -1 on that side. My x squareds, all I have is a b over on the other side. So that tells me that b has to be -1. How about my x's? I have 5 here, and I have a and c on that side. So that tells me a plus c has to equal 5. What else? I still have some pieces on the right side that I haven't used yet, right? The constants. Do I have any constants on the left side? No. So they have to equal 0, right? It has to balance with 0. So my constant pieces, I've got this b and the d. So b plus d has to balance with 0 on the left side. Okay, well this one is, we can just do algebraically, right? I mean, this is, we've already got 2 of our variables figured out. Okay, so if we know that a is 2, we can dump that in, right? We have 2 plus c equals 5, which means c has to be 3. Okay, if we know b is -1, we can dump that in. We've got -1 plus d equaling 0. So d has to be 1. So we have our ABCDs. We can go ahead and put them back into our expression here. So we have 2x cubed minus x squared plus 5x all over x squared plus 1 squared equaling, we had x squared plus 1 and we had x squared plus 1 squared for denominators. The first one had a numerator of ax plus b. So a is 2, b is -1, so 2x minus 1. Okay. The second one had the cx plus d, so 3x plus 1. We okay with the irreducible quadratic type? Okay. For the application question, it says each part of the partial fraction decomposition of a rational function plays a central role in the analysis of its graph. We can use it to describe the end behavior of the graph at its asymptotes. So we're going to start out just decomposing this, okay? But then we're going to take each of the pieces that we've decomposed it into and analyze their graphs. All right, what does it tell me about the original picture? There is one thing I want you to notice about this one that's different from all the other ones we've done, and that is that the degree on top matches the degree on the bottom. And we said in order to decompose it, the top degree has to be smaller. If it's equal to or bigger, we have to divide first. So we're going to have to do a long division to figure out what is the true remainder of this, and we only have to decompose the remainder part. Okay, so we'll brush off the cobwebs on polynomial long division. Try to contain your excitement, I know. Okay, so we are taking x squared minus 4 and we're dividing it into 2x squared plus x minus 14. Okay, anybody remember our first step? Yeah, we do focus on just the first piece in each one. So if we took that 2x squared and divided it by that x squared, what's left? That's what goes on top, right? That whatever's left, in this case just a 2. Okay? Then how do we figure out what we put underneath? Good. We times the 2 and the x squared minus 4 back together. So 2 times x squared, 2 times negative 4. Notice that I moved it over so my columns are lined up. We are going to subtract now, right? That's the next step in division. 2x squared minus 2x squared is gone. That's the intent of it. If it doesn't disappear, you did something wrong. Okay? We have an x and we're subtracting no x's, so we still have an x left. And then we have a negative 14 and we're subtracting a negative 8. So we're really adding 8. Negative 14 plus 8 would be negative 6. The x minus 6 is the remainder. I know it's the remainder because my next step would be to say, okay, let's divide it by x squared again, and I can't, right? I don't have enough x's to take an x squared out. So that's all I can do for the division, which basically means that this original rational function could have been written as 2 plus our remainder piece. And the remainder was x minus 6. We're trying to divide it by the x squared minus 4. It's just too small, so we can't. Okay? So when we do our partial fraction decomposition now, we are only going to have to decompose this. Does that make sense? Okay. So go ahead and set up your pieces. Think about how does x squared minus 4 factor. You should have broken it into x minus 2x plus 2. Yes? So how many fractions are we going to have in this? We're going to have 2. One is going to have a denominator of x minus 2. The other is going to have a denominator of x plus 2. Are those linear? Yes. So all we need for numerators would be constants. So we'll just have an a and a b over here. Okay. Next step would be to multiply this by our LCD. All right, so on the left side, all we have left is our x minus 6. On the right side, what is a getting multiplied by? X plus 2. And what is b getting multiplied by? Good. All right, so if we distribute, we have ax plus 2a plus bx minus 2b. All right, so where are my x's? I have a of them and b of them. So a plus b has to equal 1. And my constants, I have 2a minus 2b of them. And it has to balance with negative 6. This is a pretty small system. We should be able to do this algebraically, all right, just as fast as putting it in matrix format. Okay, so let's say we times the top one by 2. and combine it with the bottom one, what happens? Cancels out the b's. All right, so we get 4a equaling negative 4, which means a has to be negative 1. We good with that? All right, plugging that back in, we've got negative 1 plus b equals 1, so b would have to be 2. Okay, so my function had a 2 that we divided out, right? And then for the fraction part, that x minus 6 over x squared minus 4, we have decomposed that into 2 partial fractions. Over the x minus 2, we had an a, and we said a was negative 1. And over the x plus 2, we had a b, and b was 2. Okay? So my original rational expression could be decomposed into that. Yes? Okay. Now, I'm going to take this in pieces. Let's go back to the original way it was written. And that was, we had 2x squared plus x minus 14 over x squared minus 4. If we were analyzing asymptotes, we said the denominator factored into x plus 2x minus 2. What makes that 0? 2 and negative 2. So in my graph, those would show up as what? Vertical asymptotes. Yes? So my original function, if I were to graph it, would have vertical asymptotes at x equals positive and negative 2. What about horizontal asymptotes? How do we find those? Has to do with the powers, with the degrees, right? If the top degree is smaller, it's on the x-axis. If the top degree and the bottom are the same, yes, it's the leading coefficients. If the top degree were bigger, you didn't have any. Okay? So in our case, the degrees are the same. They're both x squareds. So we would go to the coefficients, which would be 2 over 1. So we would have a horizontal asymptote at y equals 2. We good with that? Yes? Okay. If we looked at just the different partial fractions, this one right here, top degree is smaller, so it would have a horizontal asymptote at the x-axis, y equals 0. Vertical asymptote where? At x equals 2. Okay? This one, same thing. Top degree is smaller than the bottom. So horizontal asymptote would be y equals 0. Vertical asymptote would be what? Okay. So let's look at what the graphs show us. All right? The first picture is the original function. All right? Not decomposed, just the original thing. Do you see a vertical asymptote at 2 and negative 2? Okay. Do you see a horizontal asymptote at 2? Yes? Okay. The second one is the one that had a vertical asymptote here at negative 2. So that was this one. Yes? And the third picture is this one, has a vertical asymptote at positive 2. Okay? I want you to look just at the end behavior. That means as we approach the asymptotes, where is your graph headed? So, on the second graph here, as I approach the x equals negative 2 line, on the right-hand side, I'm heading towards positive infinity. On the left, I'm heading towards negative infinity. Yes? Look at your original picture. as you approach this line, are you going up on the right and down on the left? So those match, yes? So this part of my whole piece, this partial fraction, is affecting that behavior on my graph. Does that make sense? The third picture is the one where we said we had a vertical asymptote at 2. Looking over here at our vertical asymptote of 2. On the left, we're pointing up. On the right, we're pointing down. Same thing here. Left is going up. Right is going towards negative infinity, down. So this third piece of this third graph is basically showing the effect of the 2 over x plus 2 part of it. And then what happens if we add 2, just a plain 2 to my equation? What does adding 2 at the end do? It's a vertical shift, right? So did our picture shift up 2? Instead of having asymptotes at 0, like the little pieces did, we shifted everything up 2, and now it had a horizontal asymptote at 2. Okay? So it's basically saying if you can take this big rational function, if we didn't have a graphing calculator to know what it looked like, you could look at the decomposed pieces of it to get a feel for what's happening. Okay? Don't worry, I'm not going to make you do a ton of those. Just a few. All right, last question. We are not solving it. We are just setting it up. So I'm going to pause the video here. I want you at your tables, just write all the little fractions out, but you are not solving for your ABCs. Okay? Okay, I did have a couple groups as I was walking around ask, do we have to divide on this one first, like we did on the previous example? The answer is no, because if you multiplied all those factors in the bottom out, you have x squared, you're going to have an x to the 4th, right? And you're going to have an x. That means you're going to have an x to the 7th as your highest power, which is which is bigger than the top, so you're okay. You don't have to do any division. Now, the first factor here, x squared plus 2x plus 5, can it be reduced more? So this first one is an irreducible quadratic. Yes? How about the x minus 4 piece? You're going to have a lot of different fractions that use that part, right? Because it's in there 4 times, but it is linear, right? Okay, so that one's linear, and the x plus 3 is linear. So of this, if I were going to decompose it, I would have a fraction that has the x squared plus 2x plus 5. Yes? Then I would have a fraction that has what? X minus 4. Then I would have a fraction that has, good. Then I'd have a fraction with x minus 4 cubed. I'd have one with x minus 4 to the 4th. And last I would have an x plus 3 piece. Okay? So what would go on top of my first fraction? Yes, because it is quadratic, I need a linear expression. So ax plus b. And then everything else is just linear. So I'm just going to have constants, c, d, e, f, g. We're practicing our alphabet, yes. Okay? Don't panic. I wouldn't give you one this big to do on a test. Okay? I just want to make sure we're clear on how the different types of denominators I need. We good with that? Okay. So you guys are doing day 2